Hello guys, and welcome back to my channel. And in this video here we have extra practice problem on conservation of energy, and this one's a little bit different from the other ones we've been doing in class. This involves the pendulum type of motion, as you can see from this crude drawing right here from me. But let's get started on this problem. So this problem reads: a 3-kilogram pendulum is held at an angle of 10 degrees to the ceiling with a length of 2.5 meters. What is the final velocity at the bottom of its swing? So we want to know the final velocity at this moment right here, at the bottom of its swing. And it's also being held at an angle in reference angle of 10 degrees right here, and then it's let go. Alright, so let's break down what we do know from this problem, at least. So the mass of our problem is 3 kilograms. Gravity is 9.8 meters per second squared. It's being held, so initial velocity has to be 0 meters per second. The final velocity is what's being solved. Okay, so that leaves a couple things here left. Oh, let's also write down the angle. The angle is 10 degrees here. Initial height. Actually, let's not talk about initial height just yet. Final height equals. Now, if it's the bottom of the swing, alright, if it's the bottom of the swing right here, right, that's implying that it cannot fall any further unless we cut the pendulum, but we're not going to do that. It cannot fall any further, and because it can't go any further, that's almost saying like it's at the ground. If you're at the ground, you can't fall down any further unless otherwise explicitly stated. So in this case, because it's at the bottom of the swing, we say the final height is going to be 0 meters. Let me write it down right here. Okay. Now, we're trying to find final velocity, but it seems like the initial height isn't really there either, or not given at least. Alright, so we look at our picture here. Pendulum's here. Okay, and we describe height as the vertical distance, if you will. Right. So even though this pendulum falls this way or swings that way, that's not the height. The height that we actually care about is from where we held it and as it falls vertically, like so. Okay. So let's label it properly. Between here and here, that is the height that it falls, and whatever height it's falling from, that is what we call the initial height, the height that it's falling from. Alright, but that, again, that's not explicitly given. Alright, what they do give us is the length of the pendulum, which is 2.5 meters. Alright, this is the pendulum when it's at the bottom of its path, and this is the same pendulum right here. Length equals 2.5 meters. I'm just going to write it twice to emphasize that it's the same pendulum here. Alright. They also give us an angle in reference to the ceiling. The angle is only 10 degrees. Okay, right there. Right. So why is the angle important to us? Well, we have the length of the pendulum and we have the initial height. And they give us the angle so that we can find this side right here. Okay, and I'll explain in a moment why we need this side right here. Alright, if you look at it, this drawing, if you include this side right here in red, and we can call this delta y, you realize that if we combine delta y and the initial height, you realize that combining those two things is the exact same thing as the length of the pendulum right here. Okay, combining, let me draw a better picture. Combining delta y and the initial height is the exact same thing as the length of the pendulum. Alright, so how do we write that statement down? This is not necessarily formula, this is like an observation, if you will. Delta y plus the initial height is the length of the pendulum. And if we can figure out what delta y is, we can figure out the initial height. And then once we can figure out the initial height, we can use conservation of energy formula to solve for the final velocity at the bottom of the swing. So, how do we find delta y? Well, we have to go back and refer to our trig functions. Right? Sine of the angle is defined by the opposite over the hypotenuse. But of course, the opposite and hypotenuse have actual labels in this problem. Right? The angle is just, it's actually, and probably I should mention this earlier, this region right here is a right triangle, and that's why we are able to use a sine function. Forgot to mention that earlier. Sine of the angle equals the opposite side, which is actually delta y, over the hypotenuse. Hypotenuse mean the longest side of a triangle. In this case, the long side, we have also called it the length of the pendulum. Alright, so if we do this, we do sine of 10 degrees equals delta y over 2.5 meters. Okay, when you do sine of 10 degrees and then multiply that by the length of the pendulum, you're going to find out that delta y equals 0.43 meters. Okay, and once we figure that part out, we can go back to our statement that we made earlier. Right here, and we have delta y. It's 0.43. So we can use the statement that we made. 0.43 meters plus the unknown initial height equals the length of the pendulum. And all you have to do here is solve 0.43 on both sides to solve for initial height. Right, and then by doing this, we'll find out the initial height is 2.07 meters. Okay. Now going back, well, now we have initial height finally. All right, we can go back to our information that we gathered. Initial height is 2.07 meters, like so. Now we can use our conservation of energy formula and then proceed. Now if you remember that conservation energy formula, I should write the whole thing out. I'm going to actually, just to make sure that everything is clear. 1/2 mv I squared plus mass times gravity times initial height equals 1/2 times mass times final velocity squared plus mass times gravity times final height. Right, so remember, initial velocity is 0, so we can look at this term right here. Okay, if initial velocity is 0 and you can plug it in, you'll realize, well, this whole thing goes to 0. We can kind of get rid of that. If you insist on plugging it in, that's perfectly fine. And also we said the final height is 0, and final height is at the end here of our conservation of energy formula. You realize if you plug that in, the entire thing goes to 0 as well. Well, that just leaves us with mghi, mass times gravity times initial height, equals 1/2 mvf squared. Okay, now we can go ahead and plug the known values in. And I actually might move my work down here so that I actually have more room. Okay, this is going to be, let's plug this in, 3 kg times 9.8 meters per second squared times initial height of 2.07 meters equals 1/2 times 3 kg times final velocity squared. Working out the left side of the equal sign here, we're going to get around 60.85, around there, equals to 1/2 times 3, you'll get 1.5 VF squared. And here we're going to divide on both sides by 1.5. Okay. And we are going to get, let me break this down here, 60.38 divided by, sorry, not 38, what am I saying? 60.85 divided by 1.5. We're going to get 40.56 equals VF squared. And then your last step here is to square root both sides to find the final velocity of our problem. And when you do, your answer will be I'm going to have to use this, whatever is left room here. Final velocity will be 6.36 meters per second. Okay, and that is the velocity at the bottom of the swing. Okay, this looks like a bunch of work, but I hope this video has been helpful for you, and feel free to replay it if if any concepts seem unclear. And thanks for watching, and see you in the next video.